Hello, my name is Nawalage, and in this video, I will be briefly talking to you about our recent work on cascading optical processes. This work was published in December 2022 in the Journal of Analytical Chemistry and is the first of a series of 3 companion articles published by our group. The cover art of this work was accepted by the Journal of Analytical Chemistry as well. The goal of this series of companion studies is to develop a systematic and mechanistic understanding of the effects of cascading optical processes on experimental quantification of the sample scattering, absorption, and emission properties. Light scattering is a universal matter property that is especially prominent in nanoscale or larger materials. However, the impacts of light scattering on experimental quantification of material light absorption, scattering, and emission activities have not been adequately addressed in existing literature. In the first part of the study, we will look at the effects of scattering on the experimental quantification of sample scattering activities such as molar scattering coefficients or cross-sections, scattering intensity, and depolarizations. In part 2, we hope to look at the impact of scattering on the light absorption in samples that contain both scatterers and absorbers. In part 3, we wish to look at the effect of scattering on experimental quantification of the optical properties of samples that contain absorbers, emitters, and scatterers. Numerous cascading processes can be imagined for photonically active nanoscale or larger materials, many of which are simultaneous scatterers, absorbers, and emitters. Examples of cascading processes include the reabsorption of the fluorescence photons generated by absorbing the incident photons, which further triggers fluorescence emission, the absorption of the scattered photons with and without generating fluorescence photons, and the scattering of the scattered photons, followed by other possible optical processes. Those cascading optical processes, in combination with the practical measurement constraints such as limited sampling volume, detection angles, etc., can significantly complicate spectral data analysis. Many of the models developed for correlating analyte photophysical properties with analyte concentration are developed for optically simple samples. By optically simple samples, I mean that the cascading optical processes triggered by individual excitation photons are negligibly small. The fate of the scattered photons is extraordinarily complicated, even in the simplest light scattering sample, where the analytes are pure light scatterers with no absorption or emission. The different spectroscopic methods employed in this study, namely UV visible spectroscopy, integrated sphere-assisted UV, which is termed ISUV, and LPRS, are all performed with the commonly accessible UV-Vis and spectrofluorometers. These techniques and the method for determining the depolarization are discussed in previous videos that you can access on our website. Using a series of polystyrene nanoparticles of different sizes as the model analytes, we have presented a combined computational and experimental study on effects of light scattering on the experimental quantification of nanoparticle scattering activities such as scattering cross-section, molar coefficient, intensity, and depolarization. First, let's discuss about the scattering activity and the interference of forward scattering. For samples that are pure light scatterers, the Beer's law is complicated by forward light scattering. Any forward scattered light reaching the detector leads to an underestimated experimental scattering extinction. The UV-Vis and IS-UV spectra are both acquired with the same double beam in time spectrophotometer, differing only in the detector acceptance angles. The conventional UV-Vis and the IS-UV differ only in the detector acceptance angle. The detector acceptor angle is defined as the angle between the propagation direction of the incident light and the maximum angle along which the forward scattered light can be collected by the detector. Since the acceptance angle of the conventional UV-Vis measurement is significantly smaller than that of IS-UV measurements, the UV-Vis intensity is invariably higher than the IS-UV intensity of the scattering samples. We can modify the Beer's law to include the interference of the forward scattered light. I0 is the incident light intensity. IT is the intensity of the incident photons that pass through the samples without undergoing any light scattering. IFS is the intensity of the forward scattered light. Neta is the fraction of the forward scattered photons reaching the UV-Vis detector. It is currently impossible to determine the neta value because it depends not only on the instrument acceptance angle but also on the spatial distribution of the forward scattered light. The interference of forward scattered light on UV-Vis measurements is shown with both computationally modeled and experimentally measured data. When the PSNP concentration is low, all experimental scattering extinctions are equal to its theoretical value. The upper Beer's law abiding scattering extinction limit for polystyrene nanoparticles decrease with increasing nanoparticle size. While it's impossible to estimate such an upper Beer's law abiding scattering extinction limit, we believe that Beer's law is applicable for samples with experimental scattering extinctions below 2 for samples with scatterers smaller than 400 nanometers in diameter. This conclusion is supported by the computational simulations that were conducted. In this work, we explore the concentration dependence of the PSNP scattering intensity detected with the resonance synchronous method, performed with spectrofluorometers. At low PSNP concentration, the scattering intensity increases with increasing PSNP concentration, and the shape of the RS spectra remain approximately constant. However, further increase in the PSNP concentration introduces spectral distortion. When the PSNP concentration is higher than a threshold value, further increasing PSNP concentration reduces the scattering intensity. The latter is due to the inner filter effect induced by light scattering. Inner filter effect induced by light scattering is responsible for the light loss along the photon path length before reaching the instrument sampling volume. It must be emphasized that the inner filter effect induced by sample absorption and scattering on scattering intensity measurements are drastically different. The absorption inner filter effect is an intrinsic photophysical phenomena that invariably reduces the sample scattering intensity. In contrast, the scattering inner filter effect is due to the change of the spatial distribution of the scattered light, which affects their probability to reach the detector. Moving on to scattering depolarization, it is a fundamental scatterer property that is related to the scatterer size, shape, and chemical composition. Depolarization describes the polarization changes between the incident and scattered fields. The advent of the LPRS method enables one to readily acquire the scattering depolarization spectrum across the entire instrument wavelength range. Determination of depolarization spectra and G-factor spectra are discussed in a previous video which can be found on our website. The insights from this study are important for the mechanistic understanding of the strengths and limitations of the various light scattering based parameters such as extinction, intensity, and depolarization for material characterization, including nanoparticle quantifications. Thank you for your interest.